Well, hello there. Today's lab, which is using Newton's second law to determine your weight on other planets, is a little complicated. I'm going to go over this really well in class. I'm going to work with you guys, but sometimes people are absent, so I'm making a video to help you guys understand it a little better. It's going to be really important that you read through this, and I'm going to go through and make sure I'm going to put my name on here. Oh, yeah, there's Mr. There we go. Period. So for me, that's all, and then the date. Then you're going to make sure you read through this because there's a lot of really good information in here that'll help you guide through it. Now, this is all going to be online. I'm doing this by hand just for the sake of this video. You'll be doing this on your computer. At least you'll be writing your answers in, but you'll probably also need to have some scratch paper to do some formulas and calculations. It's going to start off really difficult, and you might be learning some new math tricks with this, but you're going to find out that as you kind of move along, it gets easier and easier and easier. Pretty simply, we start off with our Newton's second law. Newton's second law is basically the force equals mass times acceleration problem. I know when you guys did the worksheet, it was acceleration as a measure of mass and force, but it's really the same formula, just reworked to solve for force. So force is mass times acceleration. Now, something we talked about is that anything that has mass has gravity. We've said it over and over and over again. At this point, hopefully you know that. Well, there's a measure, when we measure weight, weight is really a measure of your mass times the acceleration of the Earth's mass pulling on you. So anything that has mass has gravity. The Earth has mass, and thus its gravity is pulling towards you. So weight is really a force. So you're able to think of weight and force as the same thing. It's your mass times the gravity in which the Earth. It's the same formula. Force is mass times acceleration. Weight is mass times the acceleration of gravity in which the Earth is pulling towards any object towards the Earth. And this gravity right here, this acceleration due to gravity, here on Earth, I'm going to go ahead and tell you right now, 9.81 meters per second squared. That is the acceleration that anything falling towards the Earth will be falling towards the Earth. And that's given to you right here. The tricky part is that this thing right here, mass. Because this class is taking place in the United States, we don't measure in our body mass. It's not something that we normally do. We use our weight, but we use it in pounds, and this is in newtons. So it's a little odd in the United States that we use different things. So what we're going to have to do is we're going to have to take the American standards and convert those into the metric standards. So how are we going to do that? Well, keeping in mind that the Earth's gravity is 9.81 meters per second, we can just go ahead and we're weighing ourselves on Earth. So when you weigh yourself, you're going to weigh yourself on Earth. To figure out your weight, we can look at the gravity as being 9.81 meters per second squared, and then we can determine your mass from there. It actually gets a little simpler than that, taking into account that that always kind of holds. This number is always going to be the same. So your mass is really your weight in pounds times 4.54. Okay, so I'm going to move this off to the side here. So let's write this down again. Your mass, and that's going to be in kilograms. And if you went anywhere else in the world and you stepped on a scale, it's going to measure in kilograms, is your weight in pounds. And pounds, and pounds is abbreviated LBS, times 0.454, which is the conversion ratio between the two. Okay, now let's just take an arbitrary person. We won't shame anybody. First of all, you're going to have to do your own weight, and every person's lab is going to be unique and different because you guys all weigh different amounts. So your lab is going to be unique to your weight. Now, I'm not into weight shaming. I do have a scale in the front of the classroom, so if you need to weigh yourself on the scale in the front of the classroom, that's fine. If you're a little insecure about your weight, then put your ideal weight down. What weight do you want to write down? I'm going to be good with that. The actual weight for you is not important to me. What I'm looking for in this lab is that you're able to convert weights. So I'm going to put down my weight, which is last checked 215 pounds. All right, and LBS, once again, that stands for pounds. I'm going to multiply that by 0.454, and that's going to give me my mass in kilograms. You may use a calculator. I suggest for the purposes of today, don't use your phone because the phone's a little confusing. This video is going to show you how to use this calculator, and there's going to be some more complicated calculations. So let's just use the calculator that comes with Windows. If you don't have calculator here in your menu bar, you can go over to the search bar, type in calc, and it'll bring up the calculator. Make sure it's the scientific calculator. I believe you can go right here and say standard and scientific, because we will be using exponents a little bit later on. All right, I'm going to clear everything out here, and I'm going to type in my weight, 215 pounds, and I'm going to multiply that by 0.454, and that's going to give me a mass in kilograms of 97.6 kilograms. I'm going to round that to the nearest tenth, okay? Which means on my lab now, right here where it says, what is your weight in pounds? I'm going to write my weight as it is in pounds, which was 215, right? Okay. And then I'm going to put, I just figured out what my mass was in kilograms, or my mass was in kilograms, which was 97.6. Now, there's another thing that we need to kind of figure out here, is that I said that weight is a force. We just figured out the mass. Once we figure out your mass, now we could put that mass into this number, multiply it by 9.81, and that will give us our metric weight. Okay? But there's two ways we could do that. We could do it that way, putting 97.6 here times 9.81, that's going to give us this. Or I could use this other formula right here, which is doing kind of the same thing, where I'm taking my metric weight, and I am going to multiply it by my weight, which was 215 pounds again, times, and this time it's going to be, we're going to multiply that by 4.448. Okay. Once again, this number right here is the helpful conversion ratio between the two. All right. I'm going to use my calculator. Clear my calculator out. Type in 215 times 4.448, and that's going to give me a metric weight of 956 newtons. Remember, newtons is the measure of force. So that's how much force I am putting on the earth due to my weight force. So this is my weight force in metric. This would be my weight mass. 215 pounds would be my pound force, is what they would call it. Okay? So 956 is a number I can put here. And you're like, Mr. Lee, we just did this 2 different ways, and really it's the same thing. This will help later on in the lab to have both of these things done. Okay. So it's important that these 3 numbers, number 1, number 2, and number 3, all get done exactly right. All right. Now, the next thing is a little bit more complicated. This is where, so far this lab is pretty simple. The next thing is a little complicated. Before I get to the next part, I need to talk about something called exponents. Have you ever seen a number that looks like this? 2.352, and then you see times 10 to the 6th power. Okay? That's like saying 2.532. This is actually a really large number, 10 to the 6th. That's called its exponent. And really what that means is I'm taking 2.532 and multiplying it by 10 6 times. Every time you multiply a number by 10, basically the decimal point moves over 1. So if I were to write this out, 2.532, and that's a decimal point, it's not a comma. If I were to write this out normally, 2.352, basically what I'm going to be doing is I'm going to move my decimal point to make this a large number. I'm going to move it over 6 times. 1, 2, 3, 4, 5, 6. All the times that there's nothing there, I'm just going to put zeros to fill in those blanks. So you saw I moved the decimal point over 1, 2, 3, 4, 5, 6 times. That's this number right here. So that's multiplying 2.532 times 6. This is the actual number. So why do we do this? Well, we do this because we're going to get some really big numbers. And we're talking like move the decimal point over 20 times. And you don't want to have to go through, a lot of calculators can't even do that. So instead of writing 2,352,000, putting all those numbers into the calculator or using those really big numbers, we use the exponent. We say 2.5. We always put it between the first and the second number, or we usually put it between the first and the second number. And these numbers that follow usually are significant. Anything after that is probably rounded off to 0. All right. So conversely, if you see a number like this, 1.76 times, and my calculator is going to get in the way here, times 10 to the negative 5, let's say. 1.76 times 10 to the negative 5. Now what you're doing, the negative 5 just means I'm dividing by 10 5 times. Which means simply I'm going to be moving the decimal point to the left at this time. So instead of being 1.76, I'm going to move that decimal point over 1, 2, 3, 4, 5. And I'm going to put that decimal point right here, and I'm just going to add zeros to fill in those blanks. So this number is a really, really small number, which is 0.0000176. Okay? And that's what exponents are. So how do I put this number into my calculator? And this is why I suggest you guys use your Windows calculator, because every calculator does this a little different, and it's a little confusing. Especially when you see that there's this 10 to the x, everybody thinks that that 10 to the x is the same thing as 10 to the 6. No, that's not what's going on there. What you need to do is, since this is an exponent, you're going to type in 2.52. Oh, I did that wrong. Try that again. 2.352. And to get that times 10 to the 6, since it's an exponent, EXP stands for exponent. Sometimes it says EE. I know if you have a Macintosh, it says EE instead of exponent on its calculator. But you're going to click this button, and you see right here it's going to say E plus, and then you're going to type in 6. So what that means is it's 2.352 times 10 to the 6th power. Now when I hit equals, you can see it just gives me the number just like this, straight up. All right. How do we do the negative ones? It's pretty simple, same thing. 1.76 1.76, and I'm going to have that as an exponent, exp, times 10 to the negative 5. So you can put 5, and you notice there's a little plus or minus symbol there. You can hit that plus or minus symbol, and it says to the negative 5. So that means 1.76 times 10 to the negative 5. And when I hit equals, the calculator is actually going to go back and do it to look like this. Okay? So we're going to be doing exponents in this lab, and it helps to know that part as well. So the next thing we're going to do is we're going to find out how to calculate your weight on other planets. Now I'm going to do the moon. Now the moon's not a planet, it's a satellite. But we're going to do the moon as an example, and then you guys will do the other planets on your own. So the first thing you got to do is know what your mass is. You need to know what the moon's mass is, and you need to know the size of the moon's mass. And we're going to use a modified version of Newton's second law. Instead of force equals mass times gravity, we need to find out what the acceleration of gravity, which is little g here, the acceleration due to gravity on the moon, so that's that little g right there, equals the gravitational constant, which is a number I'm just going to go ahead and give you. It's 6.67 times 10 to the negative 11, which means it's a really, really, really small number, all right? Very microscopic. That's the gravitational constant times its mass, and this is the mass of the moon. Now, in space, if you have two masses, both of those masses have gravity. So this really should be the gravitational constants times mass 1 plus mass 2 divided by the r stands for the radius of the planet in meters. So why don't I have mass 1 plus mass 2? Well, we're seeing how much you would weigh on the moon. If we look at the moon's mass and we look at your mass, the moon has such a phenomenally large mass compared to you that you don't matter and you wouldn't even figure into this equation. So this is a new equation that, we've got it all spelled out here, that we're going to use to figure out first of all, the acceleration. Once we figure out the acceleration of gravity on the moon, which is going to be different than the Earth, then we can take your mass and multiply it times the acceleration of gravity in the moon and determine what your weight is from there. Okay? So, it says to complete the following chart, this is the chart right here on the next page. What is the mass of the moon? And I have that written down right here. The mass, the mass of the moon is 7.342 times 10 to the 22nd power. So that means that 10 to the 22nd, there's an exponent. That means that this number is very, very large. Okay, that means I've moved the decimal point over 22 places. So, I mean, you could write 7.34200000000. This is just a much easier way to write this. The gravitational constant, I gave you that already. The radius of the moon, and it's a little bit odd. If you go look on Google what the radius of the moon is, it's going to give it to you in kilometers. The problem with in kilometers is that I need it to be in meters, not kilometers. So meters, there's 1,000 meters in every kilometer. So if you see that it's, if you see something is 750 meters, you're going to have to add 3 more zeros on it. You have to multiply that by 1,000. That'd be 730,000 meters, okay? So in the case of the moon's radius, which is from the center of the moon to the surface of the moon's radius is 1737 times 10 to the 6th power. I didn't put the decimal point in there. I'm not sure why I didn't do that, but so what's the acceleration due to gravity? That's what you're trying to find out. All right. So we've got all the details that we need to use this formula, which I'm going to write down on this paper right here. Acceleration due to gravity, little g, equals the constant times the mass divided by the radius squared. Okay? We're solving for the acceleration. The constant, which is written right there, is 6.67 times 10 to the negative 11. And I'm going to multiply that by the mass, 7.342 times 10 to the 22. And that is in kilograms. All right. And then we're going to divide that by the radius, which is 1737 times 10 to the 6th power. And we're going to square that number. All right. Now, this is just math. How are we going to do this? Now, these exponents kind of make it a little tricky if you're not good at math. This is why, once again, I suggest you do this on your computer. Let's multiply across the top first. That's 6.67, and this is an exponent. We're going to multiply that by 10 to the 11th power, but it's the negative 11th power, so it's got to say 6.67 times 10 to the negative 11th power. Okay? Then we're going to hit multiply, and it's going to automatically change it, so that's what negative 11 looks like. We're going to multiply that by the mass of the planet, 7.342 times exponent times 10 to the 22nd power. We can leave that positive. And we get this number. And so far I've not figured out how to get Windows to tell me what the exponent is. So I'm going to have to figure out where to put the decimal point because I don't want to write all those numbers out on my paper. So basically what you're doing is you're going to move the decimal point over 3, 6, 9, 12. That will come to 4 point, and I'm just going to round off 90 times, so 4.89 instead of 4.89, I'm just going to say 4.9. I'm going to round that up, okay? Times 10 to the, and what did I just say, 12th power, all right? Because I moved the decimal point over 12 times. Now we have to do the denominator, this part right here, okay? To get the denominator, remember this is squared, and I forgot to write that in there. Let's clear this out. And we're going to say 1737 times 10 to the 6th power. But this is squared. So we look on here, you'll have a little x to the 2. That means squared. So that just basically means we're going to take this number and multiply by itself twice. And that, whoa, look at that big, big number. 3, 6, 9, 12. You know, I think I made a mistake. I believe this should have been, and I kind of thought maybe it was 1.737 times 10 to the 6th power, and I'm going to square it. 3, 6, 9. Yeah, this should have been a decimal point right here. So my notes, I forgot to put a decimal point there. I thought so, and I was looking at that, and you might have heard me hesitate a couple of times because usually when you use an exponent, there's a decimal point right there. So this should be 1.737 times 10 to the 6th power, which once we square this number, we're going to get this really big number. And if we look, once again, we're going to move that decimal point, 3, 6, 9, 12. So that would be like writing 3 point, and I'm going to round this off, 3.02 instead of 17. I'm going to just take that 1 right there and round it off to 7, brings it up to a 2, times 10 to the 12th power. Okay, so this number and the number on my calculator are essentially the same number, okay? All right, so now we've got to take 4.9 times 10 to the 12th power, divide that by 3.02 times 10 to the 12th power. So let's do this, 4.9 exponent 12th power divided by 3.02 exponent 12th power. Now, if you've been paying attention to math, there is an easier way of doing this. If you have 10 to the 12th power and 10 to the 12th power, they cancel each other out. But I don't want to confuse anybody, so we're just going to go ahead and do it this way. If you can math better than this, you do you, all right? And that comes to, excellent, I got the right answer. The gravitational constant is going to be 1.62, and it's already, we don't need it, don't worry about all these numbers, that's just after, that's like impossibly small numbers. I'm just going to go to the nearest hundredths of the decimal point, and this is not an exponent, and the decimal point is already in place, and you notice that there's no e to the whatever, okay? So this is 1.62, and since it's an acceleration, remember this is meters per second squared. That's how fast things fall on the moon. Okay, so now we can go back to our lab, and we can type in 1.6, and oh, this was 1.7, that was a mistake. 1.62 meters per second squared. By the way, that was in meters, and that was in kilograms. Should write my units on here at all times. Oops, I didn't write that on there. Okay, so 1.62, this was the answer I just added. Sorry, that was off camera. That's what we were trying to answer for. Now, if we go through, we can go back to our weight formula. Weight equals mass times gravity. Remember that? Whereas weight is your weight on the moon. Mass is the mass that you calculated earlier, and g is your gravitational constant. So what was your mass in kilograms? Well, you figured that out right here. Your mass in kilograms for me, my mass was 97.6. Everybody's going to have a different mass. So 97.6. Let me bring that number down. What is the gravitational acceleration on the moon? That is this number from the moon question, question number 4. That is 1.62 meters per second squared. So 1.62. So what's your weight? Well, we use this formula. Use a piece of paper. Your weight is, get you on the screen here, your mass times your gravity. Okay? So we're trying to solve for weight. We know that your mass, or my mass, was 97.6. All right, and that was in kilograms. Times gravity, which was 1.62. And that was in meters per second squared. Okay, 97.6 times 1.62. I can put that into my calculator, figure it out. 97.6, which was my mass, times 1.62, which is the acceleration of gravity on the moon. And that comes to, the force you would be applying on the moon would be 158, and we'll just round off to the nearest whole number. And this is in newtons. This is not pounds, okay? So you don't weigh 158 pounds on the moon, you weigh 158 newtons. Okay, so we're going to write 158 newtons. All right, that's your metric weight. But remember, we're going with how many pounds. More of us are more familiar with pounds. So what was your metric weight from question 5? Your metric weight on the moon was 158. My metric weight, not yours. Your number's going to be different. Okay? How many pounds is that? Well, remember, we had this formula from earlier, way back on the first page. We had this formula right here. I slightly modified that formula. You're going to use it as your weight in pounds is your metric weight, which is 158, divided by 4.448. So I'm going to clear this out. 158 divided by 4 point, I'm getting this number from right here, 4.448. That's your conversion ratio. And what that comes out to is 30, we'll just go say 36, I'm going to round off to the nearest whole number, 36 pounds. Okay? That means if I weigh 215 pounds on the Earth, I weigh approximately 36 pounds on the moon. Why is that? Well, the moon has a lot less mass, so it has a lot less gravity. It's not pulling me as hard, so I don't weigh as much. So you can imagine if you were to jump as a 215-pound man on the Earth, you're not going to get very high. But if I were to jump with the same muscle mass I have now, but I'm only weighing 36 pounds, I'm going to jump a lot higher on the moon than I would here on the Earth. Which would be wonders for my back. I often would feel like I should go to the moon and do that. Okay, the next part of the lab, you have some questions. I kind of just answered number 7. Number 8 and number 9, these are things that we've kind of talked about in class. And then we're going to get to question number 10. And what you're going to do with question number 10 is you're going to figure out for every planet in the solar system. And you're like, Mr. Lee, some of those aren't planets. There's Mercury, Venus, Earth, Mars, Ceres. What the heck is Ceres? Jupiter, Saturn, Uranus, Neptune, Pluto, and Eris. Well, here's the sticky widget here. The Pluto technically is not a planet, but I asked my class the other day, do I include Pluto or do I not? And they were very adamant about me putting Pluto in. Well, I'm sorry, if I have to put Pluto in, I'm going to put in some of Pluto's buddies. So if Pluto is considered a planet, then the large asteroid between Mars and Jupiter, Ceres, and you can find out it's not that large, is also a planet. And beyond Pluto, the planet that they discovered right before they changed the status of Pluto is a planet named Eris. You guys are probably lucky that I didn't put Maki, and Haumea in there. The reason I didn't put those planets in there as well, because they are all dwarf planets along with Pluto, Eris, and Ceres, was because the information is so sketchy because they're so far away that we're not really sure what their mass and radiuses are. Okay, but here we have their mass. Notice the exponents. Okay, you see Mercury is 3.30 times 10 to the 23. That means you move that decimal point 23 spots. Jupiter is times 10 to the 27. So you look at Mercury and say, Mr. Lee, Mercury is 3.3 and Jupiter's 1.8. Isn't Jupiter bigger than Mercury? Yeah, that's because of this number right here. It's so much bigger that we're only going to move the decimal point over 23 spaces here. Jupiter, we got to move 27 places over. So yes, Jupiter has a much larger mass. And you can also see that this goes to 10 to the 6 versus Jupiter, which is 10 to 7. That's a whole power of 10 higher difference between the two. Okay, so there's your planet mass. There's your planet radius. And this is in meters. What you need to do is tell me what the acceleration due to gravity is, what your weight on that planet will be in Newton force, and what your weight in pound force is going to be. So really, this stuff is the exact same things that we did here, okay? You're going to need to figure out the acceleration. Whoops. The acceleration using this formula, acceleration is the gravitational constant, doesn't change. The mass, okay, this is the thing that does change. This mass right here, this is going to be the mass of whatever planet that you're looking at. So this number right here is going to be the thing, this number and this number are the two things that change. The mass of the planet and the radius of the planet. You're going to, instead of putting the moon numbers in there, you're going to put these numbers in there. Okay? And then you're going to calculate it out, and you're going to get your gravitational constant, and that's what you're going to put in this column. And then you're going to use that gravitational constant to do what we did here. Weight equals your mass times that gravitational constant to find out what your metric mass is, and then you're going to figure out what your weight in pounds are going to be by using the other formula. Okay? So you're going to do that for each planet. It's going to be kind of trying the first couple of times, but once you start figuring out that there's a pattern, by the time you get to the bottom of this, it's going to be like, oh, this is really, really, really simple. All right? From there, you have a couple more questions to answer. I'm going on to the next page. I lost my next page. Oh, it's way over here. And on to the final page, there's a few questions to answer. And then this last part, don't be freaked out by this part. This part's really easy. You're just going to take your weight in pounds, which is right here, and transfer it over here. Now notice I got rid of a few of the planets. You'll find out why when you go to do the lab. But you're going to write all that data that you collected. So you've already done this part. Then you're going to go to this website right here, and it's going to tell you automatically, it's going to do the calculation for you automatically what your weight is in pounds. And you're going to check to see if you were right. Now, you're going to be, because these sources are slightly different and rounding off to the nearest decimal point and stuff like that, that's going to change your data. So if you say that on Mars you weigh 125 pounds, and the calculator says that you weigh 121 pounds, that is acceptable. But if you say on Mars that you're 125 pounds and it comes out to be 180 pounds on Mars, well, then you know you did something wrong, and you might want to go back and visit your answer to this question. Okay? And that's pretty much it. Double check. This is just right here to double check your answers here to make sure you did things right. If you have questions, make sure you come and ask me, because I know this is a difficult thing and we're using math. Go back and visit this video often. You can pause and go forward as you like. Good luck, everybody. I love you guys. You guys take care, and I wish you guys all the best. Goodbye.